Quantum Entanglement, an Analytical Exploration. Historical context and theoretical foundations. The origins of quantum entanglement. Quantum entanglement was first described in a 1935 paper by Albert Einstein, Boris Podolsky, and Nathan Rosen, commonly referred to as the EPR paper, as a theoretical problem to question the completeness of quantum mechanics. The EPR paradox highlighted that if quantum mechanics were complete, then it must either be non-local or allow instantaneous communication, which contradicts the theory of relativity. In response, Erwin Schrödinger coined the term entanglement, or Verschränkung in German, to describe this peculiar connection between particles. Quantum superposition and measurement. At the heart of quantum mechanics is the principle of superposition, where a particle exists in all possible states simultaneously until measured. When a measurement is made, the wave function collapses to a single state. Entanglement occurs when the wave function describing a multi-particle system cannot be factored into independent wave functions for each particle. Instead, the system must be described as a whole, meaning the measurement of one particle's state instantaneously determines the state of the other entangled particle. In 1964, physicist John Bell formulated Bell's theorem, which provided a way to test the predictions of quantum mechanics against those of local hidden variable theories. Bell's inequality, derived from his theorem, established that no local hidden variable theory could reproduce all the predictions of quantum mechanics. Subsequent experiments, starting with those of Alain Aspect in the early 1980s, confirmed the violations of Bell's inequalities, supporting the quantum mechanical description of entanglement and ruling out local realism. Quantum entanglement, at its core, is a physical phenomenon that occurs when pairs or groups of particles interact in ways such that the quantum state of each particle cannot be described independently of the state of the others, even when the particles are separated by large distances. This interconnectedness is what makes entanglement so fascinating and, well, mysterious. Mathematically, entanglement is represented using the formalism of quantum mechanics. This involves complex vectors and matrices, often described in terms of wave functions and probability amplitudes. The mathematics can be, admittedly, quite intricate, but it provides a powerful framework for predicting and understanding the behavior of entangled particles. All right, let's dive into the different types of entanglement based on the systems involved. First, we have pure state entanglement. When a system is in a pure quantum state, it is fully described by a single wave function. Next, we encounter mixed state entanglement. In this case, when a system is in a statistical mixture of states, the description involves density matrices. And then there's multipartite entanglement. This involves more than two particles, such as GHZ states and W states, which are critical for complex quantum networks and computation. Now, let's talk about entanglement measures. Quantifying entanglement is crucial for practical applications. Common measures include entropy of entanglement, where for a bipartite pure state, the von Neumann entropy of the reduced density matrix provides a measure. Then, we have concurrence and negativity. These measures are used for mixed states and provide information about the degree of entanglement. Lastly, there's entanglement of formation. It quantifies the resources needed to create a given entangled state. Moving on, let's discuss the implications and interpretations of quantum entanglement. Non-locality and causality. Entanglement implies non-local correlations that seem to violate the principle of locality, a cornerstone of classical physics. However, it does not allow faster-than-light communication preserving causality. The correlations become apparent only when the results of measurements on entangled particles are compared, which requires classical communication. The EPR Paradox and Realism. The EPR paradox challenges the concept of local realism, the idea that objects have definite properties independent of measurement, and that information cannot travel faster than light. The experimental violations of Bell's inequalities suggest that at least one of these assumptions must be false, leading to various interpretations of quantum mechanics, such as the many worlds interpretation, objective collapse theories, and Bohmian mechanics. Decoherence and environmental effects. In real-world scenarios, entangled states are susceptible to decoherence, where interactions with the environment cause the system to lose its quantum coherence and behave more classically. Understanding and mitigating decoherence is vital for practical quantum computing and communication. Applications of quantum entanglement. Quantum computing. Entanglement is a fundamental resource for quantum computing. Quantum algorithms, such as Shor's algorithm for factoring and Grover's search algorithm, leverage entanglement to achieve computational speedups over classical algorithms. Quantum gates, such as the CNOT gate, create and manipulate entangled states, enabling the construction of complex quantum circuits. Quantum cryptography. Entanglement provides the basis for quantum key distribution, or QKD protocols, such as BB84 and E91, which offer theoretically secure communication. In QKD, entangled particles are used to generate and share cryptographic keys between distant parties, ensuring that any eavesdropping attempt will disturb the system and be detected. 4.3 Quantum teleportation. Quantum teleportation allows the transfer of a quantum state from one particle to another distant particle without physically transferring the particle itself. This process uses entanglement and classical communication to achieve state transfer, with potential applications in quantum communication and networking. 4.4 Quantum metrology and sensing. Entangled states enhance the precision of measurements in quantum metrology. Techniques such as quantum lithography and interferometry exploit entanglement to achieve higher resolution and sensitivity than classical methods, with applications in imaging, timekeeping, and fundamental physics experiments. 5. Experimental realizations. So, photonic entanglement. Photons are, the most commonly used particles for entanglement experiments due to their ease of manipulation and detection. Techniques such as spontaneous parametric down conversion, or SPDC, in nonlinear crystals produce entangled photon pairs. These experiments, they've demonstrated violations of Bell's inequalities and enabled practical applications like quantum key distribution, or QKD. Now, let's talk about atomic and solid-state systems. Entanglement has been realized in various atomic and solid-state systems, including trapped ions, quantum dots, and superconducting qubits. These systems offer advantages such as long coherence times and integration with existing technologies, making them promising candidates for scalable quantum computers. Moving on to macroscopic entanglement. Recent advances have explored entanglement in macroscopic systems, such as entangling the vibrations of microscopic mechanical resonators. These experiments, they really push the boundaries of quantum mechanics and investigate the quantum classical transition. Now, let's dive into the future directions and challenges in the field of quantum entanglement. As we look ahead, it's clear that this area holds immense potential, but it's not without its hurdles. Researchers are continually pushing the boundaries, seeking new ways to harness this phenomenon for practical applications. However, there are significant obstacles to overcome, such as maintaining coherence over long distances and developing robust error correction methods. These challenges, while daunting, also present exciting opportunities for innovation and discovery in the years to come. 6.1. Scalability and Integration. Scaling up quantum systems while maintaining coherence and entanglement is a significant challenge. Techniques such as error correction, fault-tolerant computing, and hybrid quantum classical systems are being developed to address these issues. 6.2. Quantum networks and the quantum internet. Building quantum networks that distribute entanglement over long distances is crucial for future quantum communication and computing. Quantum repeaters and entanglement swapping techniques aim to extend the range of entanglement distribution. 6.3. Fundamental tests of quantum mechanics. Entanglement continues to provide a platform for testing the foundations of quantum mechanics. Experiments with ever-increasing precision and novel configurations test the limits of non-locality, realism, and the potential existence of hidden variables. Conclusion. Quantum entanglement stands as one of the most fascinating and revolutionary concepts in modern physics. From its theoretical inception to its experimental realizations and practical applications, entanglement challenges our understanding of reality and offers unprecedented possibilities for technology. As research progresses, the exploration of entanglement will likely continue to yield new insights into the nature of the universe and pave the way for the next generation of quantum technologies.